Hi, this is Beth Faber from the Hydrologic Engineering Center, and this is part 3 of Uncertainty and Frequency Estimates. This is the 8th lecture in the course on Statistical Methods in Hydrology. Right. In our list of topics, we've gotten to confidence intervals. And confidence intervals are really straightforward now that we've already talked about sampling distributions, because a confidence interval just spans some portion of the sampling distribution. Right? So if we've defined a sampling distribution for an estimate of a distribution parameter, down here is a PDF, well, we note that the area under a PDF is equal to probability. So if I want a 90% confidence interval, I want to span 90% of the likelihood, right? 90% of my distribution around the distribution parameter, right? So I could knock 5% off of either tail of this distribution to leave 90% in the middle, and that gives me an interval that spans a 90% likelihood. Right, so that's how confidence intervals work. Now, what I just described would be what's called a centered confidence interval. So I took 5% off of either tail to leave 90% in the middle. There's also one-sided intervals where we would take 10% off of either tail and leave all the rest in the other direction. And we might see some of those this week. So let's start with the sample average as an estimator for the population mean, because that's what we built our sampling distribution around. Remember, the sampling distribution was approximately normal, right? As n goes to infinity by the central limit theorem, it would be exactly normal. It's easier to work with the standard normal distribution. Well, at least it used to be easier to work with the standard normal distribution when we had to look things up in tables. Right, so switching to the standard normal distribution that has a mean of 0 and a standard deviation of 1. Here's my standard normal PDF, and we're going to span 90% of the area in the middle, defined as 1 minus alpha. That leaves alpha equals 10, and we're going to knock the 5% off of either tail by noting where my z, my standard normal z, is equal to z5 and z95. Right? Now, to get a standard normal variable, we're going to take our normally distributed x bar and subtract its mean and divide by its standard deviation, right, to leave ourselves a mean of 0 and a standard deviation of 1. So the sampling distribution of x bar, we said, was unbiased, and so its mean is equal to the population mean. And we saw that its standard deviation, or standard error, was equal to the population standard deviation divided by the square root of n, where n was the sample size from which we're estimating the population mean. Okay, so this is now a statistic that is standard normally distributed. So I can put that statistic in the middle of an expression, right? For the standard normal distribution, my Z5 and my Z95 are equal to minus 1.645 and positive 1.645. So I can say that this statistic is between those two values with a 90% probability. Now, since I want an interval for mu, I note that I have mu in my statement, but I'm going to need to isolate it. But before I do that, the distribution is normal as n goes to infinity. But if we've got a smaller sample, it might be smart to use a smaller sample approximation to the normal distribution. Right? So you might remember the student's t distribution from your statistics course in college. So student's t is a small sample approximation to the normal distribution. It is based on sample size n, because as n goes to infinity, the student's t distribution will just go to normal. But as n is smaller, t is a little bit farther from the normal distribution. Right now, fun story about students' t. It's not a distribution that only students use. It was actually developed by a gentleman named Gossett and published back in 1908. Gossett worked for Guinness Brewing Company, and he was interested in small samples because he had small samples with his vats of beer. And he was a bright guy, and he developed the small sample approximation theory, and he wanted to publish it, but Guinness, his employer, would not let him publish because they were afraid of trade secrets getting out. So he finally got permission to publish his work under the pseudonym Student. So that's why we have Student's T instead of Gossett's T, right? So moving on, using Student's T distribution, we've got the T distribution for n minus 1. And we again have 90% in the middle, 5% knocked off of either tail, or if we had 95 in the middle, we'd knock 2.5% off of either tail. So this is general. We've got our statistic again in the middle of our expression with now the T for 5 and T for 95 for our sample size on either side. So the likelihood of our statistic being between T5 and T95 is 10%, is 90%. Again, we're going to isolate our mu and rewrite the equation with mu in the middle. So here it is, mu in the middle, and we've moved everything else to either side of the expression. Now, I'm not going to talk very much about frequentist versus Bayesian statistics, but this is frequentist or classical statistics. So we're saying that the confidence interval in this case is a random variable that changes with the random sample. Right? In Bayesian statistics, we'd instead be saying that the population parameter was the random value. I'm not going to say much more about it than that, but we might hear a little bit more about Bayesian statistics from Greg this week because it's a really useful paradigm for doing probability estimates. Okay, so here's a quick numerical example. Right, in this case, we have a sample mean of 1.1, a sample standard deviation of 0.47, sample size is 19, we want a 90% interval, right? So if sample size is 19, n minus 1 for our t-distribution is equal to 18, so the t-values are plus and minus 1.734. Right, putting those into our expression gives us a confidence interval of 0.91 to 1.29, right, as a 90% confidence interval around the sample mean. And this is a table of the t-distribution, one side of it that you'll find in every textbook. Note that the degrees of freedom go down this column and the probabilities go across the top, and these tend to be probabilities further out in the tails because that's what we're often using the t-distribution for. Right? So that was confidence intervals. Next, we'll move on to the intervals or distributions around frequency curves themselves. So we just spent some time looking at the uncertainty in the estimate of the sample mean from a limited sample size. And now we're going to move to estimating the uncertainty in the entire probability distribution from the same limited sample size. So remember in the Monte Carlo simulation lecture, we looked at the relationship between the sample size and how well it represented the probability distribution it comes from. So for Monte Carlo simulation, we were generating a random sample and looking at how large we had to make that synthetic sample in order to replace the probability distribution well. Now we're working from the other direction. Now we actually have a random sample. We don't know our probability distribution, and we want to know how well we can estimate it, right? We can't just generate more sample members at will like we did with Monte Carlo simulation. We have to take the sample that we get, right? So here we have sample of size 25, 100, 1,000, and it's pretty obvious that the larger the sample, the better it represents the probability distribution. We can't make our sample larger. In hydrology, we're often collecting data over time, right? We don't get more data until we wait for more time. So instead, we're just studying how much uncertainty we have due to the fact that we have a small sample. Okay, so back to the Monte Carlo simulation or statistical experiment that we did at the beginning with the 1,000-member sample, but now I'm taking a distribution and I'm only going to make samples of size 30 in this case. So I've got this pink distribution. Maybe instead of a made-up known distribution, maybe this pink distribution is my best estimate frequency curve from the sample that I do have. My sample happened to be a size 30, so now I want to explore how much uncertainty there would be with other samples of size 30, right? So I'm going to do something that is sometimes called a parametric bootstrap, and it's just the same Monte Carlo simulation that we did before. We're starting with the pink curve, and we're generating 30 uniformly distributed 0 to 1 random values. We place them on the probability axis. We bring them up to the curve and across. In these particular 30 random values, my smallest one was 0.004. That gave me a value all the way up here. But my next step is to use these 30 values as if I only had a 30-member sample and I don't know the original distribution. So here I've plotted my 30 values as if they really were a 30-member sample. So that large event now looks like it's a 1 in 30. Right? I also fit a probability distribution to the data, and I get a line that's quite a bit higher than the original distribution. Right? Now I'm going to put that one aside, and I'm going to do it again. Here's another 30 random values. In this case, my smallest probability amongst my 30 values was 0.072. Right? So now when I plot those values as a 30-member random sample, it's going to plot further to the right, as a 1 in 30 as opposed to a 1 in about 16. Right, so now my fitted distribution is lower than the original. Here's one more, and the fitted distribution is just less variable than the original. Right, if I do this a few hundred times, my pink distribution has turned green in this picture. But if I do this a few hundred times and I plot all of those distributions that I just generated, I get something like this. Right, they span the original curve, but they have spread. And these probability density functions that you should imagine as coming out of the page, they represent the uncertainty or the spread in the results that I see for each exceedance probability. Okay. So remember, we noted that for many sample estimates, including probabilities and quantiles, they're proportional to 1 over the square root of n, which means as n gets larger, the estimates get better. So other things that the estimate of uncertainty is going to vary with for a frequency curve is the distance from the sample mean, right? So the uncertainty is going to increase with the distance from the mean, meaning if I back up, looking at the middle, my uncertainty is smaller. But as I get farther away from the middle of the distribution in either direction, my uncertainty gets larger. Right? Uncertainty also increases with variance or standard deviation. So here's two distributions that have the same mean and the same skew, but the green one has a much larger standard deviation or variance, right? That's why it is steeper. And you can see if you look at 90% confidence intervals that the uncertainty is wider for the green with a higher variance. And finally, the uncertainty increases with the absolute value of skew, meaning as skew gets further from 0, the uncertainty gets greater. So positive skew is going to give us uncertainty at the upper tail of the distribution, and negative skew is going to give us more uncertainty at the lower tail of the distribution. Okay, so in Bulletin 17b, the sampling distribution that was assumed for quantiles of the log Pearson type 3 distribution was one that's called the non-central T distribution. Non-central T meaning that it was a asymmetrical or skewed distribution as opposed to a normal distribution, right? So if this were a frequency curve and this is a quantile, here's a PDF of uncertainty like I showed on the previous slide. And with A at the bottom and B at the top, to locate it as we move it to the bottom of the screen here and have A on the left and B on the right. So we're seeing that at the upper tail, we have a positively skewed sampling distribution for, say, the 1% flow. Instead of using the non-central T distribution, we could produce the same result with the Monte Carlo simulation with the random sampling that we just did, right? So here was our distribution with our many estimates of sample size 30 from that distribution. Right? They've got these asymmetrical distributions that we can estimate directly from these samples. They've got that positive skew. We can, to make confidence intervals, we can span 90% of the middle, which is 5% off of either tail. We do that for these distributions all the way along the curve and can draw a 90% confidence interval, right? So in this case, we did it by Monte Carlo simulation instead of just by assuming a sampling distribution like the non-central T. I'm going to label these as lower and upper just to give one more view on this page. So this would be a distribution around, say, the 1% flow, and we're going to have the low that knocks off 5% and the upper that knocks off 5%, leaving us a 90% interval in the middle. So I mentioned that Bulletin 17b used that non-central T distribution, and that is based on the log normal distribution as opposed to the log Pearson type 3 distribution. The log normal distribution doesn't have skew or log space skew as a parameter, and so it doesn't recognize uncertainty in the skew. right? And if it doesn't recognize the uncertainty, it doesn't include the uncertainty and skew in the confidence intervals. So those confidence intervals are underestimated to some degree, and underestimated more for values of skew that are farther from zero. In 17C, the expected moments algorithm does produce confidence intervals that are more correct in this aspect because they do recognize the uncertainty and skew. They also incorporate regional skew and historical information at the same time, right? So the confidence intervals in Bulletin 17B, as I mentioned, really have a lot more information in them and are more accurate. Right, so let me go back to this Monte Carlo simulation where we sampled 30 members at a time from our distribution and refitted distributions in something called a parametric bootstrap. And let's look what happens to this as the sample size gets bigger. This is 30 member samples. If I double that to 60 member samples, everything is a lot closer to the original curve. If I double it again to 120, it is that much closer yet, right? So this is 60, this is 30, right? Back to 60, back to 120. So we're seeing that with a sample of size 120, every estimate of the frequency curve is that much closer to the original, and our confidence intervals are that much narrower. Okay, so I'm going to just take a quick moment to mention expected probability before moving on to the next video. Okay, so back to our original picture. I've been describing the uncertainty in the frequency curve as an uncertainty in the flow for a given exceedance probability, right? But we can also note it as the uncertainty in the exceedance probability for a given flow. So note I've turned the PDF, which still comes out of the screen, I've turned the PDF sideways, right? And this is just as legitimate a description of the uncertainty. Right now, I'm going to zoom in on a little bit and note that the fitted frequency curve gives us a median estimate of the exceedance probability. And we had talked about unbiased estimators, and an estimator is unbiased when the mean is correct, right? So we would rather use an estimate that has the mean probability rather than the median probability. So what we're going to do in this distribution is just move the curve from the median to the mean to give us an unbiased estimator. Okay. Looking at the whole frequency curve, we're going to move from the black curve, which was fitted, over to the dashed blue curve, which is now the mean estimate or unbiased estimate of the frequency curve. This is called the expected probability adjustment. Okay. As I mentioned, it makes the probability distribution unbiased. It's recommended to use the expected probability curve when the uncertainty isn't going to be carried further into the analysis. So you can imagine a sensible place to do this would be in describing the 1% flow to describe a 100-year floodplain. Unfortunately, back in the 90s when this theory was in discussion, FEMA didn't agree with using the expected probability adjustment for flood mapping, and so it was not used for that purpose. Right. Also, in any analysis that does incorporate the uncertainty in the frequency curve, we don't need to use the expected probability curve, right? Because we get the same effect by bringing the asymmetrical uncertainty further into our analysis. So some examples are HEC software, FDA, and WAT, and the RMC software, RFA. All of those use the uncertainty around the frequency curve in the analysis, and since they're using that skewed distribution of uncertainty, the effect of moving from the median to the mean is already present. So for those uses, we don't use the expected probability curve. However, a dam safety PA does need to use the expected probability curve. Okay, so an important thing to note is that once we've made the expected probability adjustment, our curve is no longer a log Pearson type 3 if that's what we started with. How do we compute the expected probability curve? Well, in Bulletin 17B, there was an adjustment, and the software that performed 17B did that adjustment for us. But remember, that adjustment was done without uncertainty and skew, and so it wasn't adjusted quite far enough. Right. Another approach would be to integrate the uncertainty CDF. Right. So remember, I said if you have a CDF, the area between the CDF and the probability axis is an estimate of the mean. Right, so that's one way to get the mean, but to get that CDF of uncertainty, at each probability or at each flow, we can do that by doing the Bulletin 17C analysis over and over again with different pairs of confidence intervals. So the default is a 90% confidence interval, but you could do a 30, 40, 50, 60% confidence interval, get all of those values and build the CDF of uncertainty at each flow or at each probability, and then integrate them. And that method is referred to as I cubed. Finally, you could do something similar with the Monte Carlo simulation that we just looked at that created the confidence intervals, right? Sample of size n to create the frequency curves, but then we'd go back to each of those frequency curves and generate new samples from them, right? And then we can pool all those values and plot all those values as one sample, and that gives us the mean estimate as well. So that looks like this. If our original distribution was black, I would have resampled with samples of size n to get an array of different frequency curves, and of wrinkly black lines would be the 90% confidence intervals from all those different curves I'm not showing. But if I then resampled from all those curves to get more data points, then the blue dots are the expected probability curve. And note it is higher than the original curve up at the top and lower at the bottom. Okay, so that is the end of the third video. And in the last video, we'll talk about uncertainty in graphical frequency curves.